So, just to complement, my name is Yann. I'm a software engineer, and this is David, and he's a DevOps, basically, and we both work at the same team, which is in charge of big data-related products at OVH. We are here to talk to you about change data capture and how Apache Flink basically helps our company become a more data-driven company. So just a quick word about our company, OVH, because it's not that famous. We are a hyperscale cloud provider, sorry. We have about 1.5 million customers throughout the globe, and we have about 29 data centers at the moment, which this number is still increasing. And the story we are going to tell now with this presentation is basically how we grew to this size. So, like any other company, when we need to grow, basically we need investors, because we need to raise some funds and stuff like that. So that's what we did, and in order to get investors, we needed to produce a lot of KPIs to basically guarantee that our company was safe to invest in, and the market we were trying to attain was a good, safe market as well. But once we produced this KPI for our investors, our top management also saw that it was very easy to take these KPIs and continue processing them day after day to basically drive the business itself. So that's what they asked us to do. They asked us to create KPIs and to make them, to compute them as close as possible to real time. So this is the story we are going to talk here. So when OVH started in 1999, we had very few services and very few databases to manage. But of course, as we grew, there was a lot of new products that came into our ecosystem, and with each new product, a lot of databases spawned as a result. So just a quick word here, when we are talking about data, we are talking about OVH own data, not our customers' data, of course. So at the moment in production, to manage all our products, we have about 200 tables, databases, which contain about 15,000 tables, and each manipulation we get about 10 million events per day in all our production. These 200 tables are spread across all our data centers, of course, because they help manage products. So if one data center falls for any reason, we don't want other data centers to be impacted, and customer service in these data centers to be impacted as well. So basically, we now have a question to answer here, which is, how do we get the data from these databases, which are spread to all our data centers, to our BI team so that they can produce these KPIs?
So the solution is to replicate all of this data at one place. And for that, we created an HDP cluster. HDP is a Hadoop distribution from Hortonworks, and we installed it on top of OpenStack instead of traditional bare metal servers. So now, how can we load all of our data into HDFS?
So, sorry, we're going to switch page.
Yeah.
So basically, here to answer this question on how to load our data, there was a lot of stuff existing in the market at the time when we started developing this pipeline. Most common one would be Scoop at the time. Now you have stuff like Debezium. But we had two constraints that was imposed to us. First one was to be as close as possible to real time. So that means that we would prefer streaming and not batching. And second one, our DBAs are quite adamant that they don't want any Java-based product to touch the database. So any Java-based product should be out of the equation. So at the time, there wasn't that many alternatives that we could afford at OVH. So instead, we decided to create our own, basically. So first, we needed to find a way to stream data from our databases and do something with that later. So what we decided to create is a Go programming program, which is going to be spawned inside containers, and which is going to connect to our source databases, which are mainly MySQL, and behave like a slave. This way we can interact with the bin log associated with this database. This way we are going to get all the events that are, the new events that are going to be created inside this database, and we will be able to process them. Each event is then sent into a Kafka queue, and that's it. But that's not enough. And why isn't that enough? It's basically because the bin log doesn't contain all the data of the databases, but only a certain lifespan. So if you want to basically get all the data from your databases and put them inside our data lake, we also needed to implement a query mode. to basically make a dump. So sometimes we are going to do a huge select and import all the data. This goes as well inside a queue in Kafka queue, and that's about it. So with that, we have another piece of the puzzle here. We know how to extract our data, but there is still stuff missing. Of course, we have Kafka. We have put all our data inside Kafka. How do we put it then inside AGFS? And so this is where, of course, Flink is going to help us tremendously. So in addition to just reading data from Kafka and putting inside our AGFS storage, it's also going to do a lot of transformation because we have a lot of databases that haven't been created by the same person. So we have heterogeneous data types. For instance, date can be a date time, timestamp, string, and lots of different kind of strings. So here in Flink, we're also going to do some cleansing of all the data to make sure that when we insert it inside our AGFS sink, everything is going to be formatted the same way. Also, you know that Flink needs a cluster to house it, basically. So being a cloud provider, we had many solutions. We could have done a bare metal if you wanted. We could have done an Apache stack. But here we have an HDP stack. So we can also include Flink and make it run directly inside it with the help of Yarn. And that's what we decided to do. So we have Flink on Yarn. This way we are completely integrated inside our HDP stack. But there is a small problem with that, because there is something we didn't talk about, our HDP stack.
In fact, our HDP cluster is a little bit customized. First, we activated and configured the Apache Ranger in order to have fine-grained ACLs until the column of the table, for example. And besides this HTTP cluster, we install FreeAPI. FreeAPI is a tool that comes from the Red Hat tool ecosystem. And FreeAPI allows us to centralize all the users' management. Furthermore, FreeAPI can host the KDC, and KDC is the main component of Kerberos. Because yes, all of this cluster is fully Kerberized. Why Kerberos could be a problem for us, as Yann said just before, we have to run our Flink jobs on top of Yarn. Our Yarn is one Hadoop service, and all of Hadoop services are protected, secured by Kerberos. So we have to find a way to, we have to deal with that. For example, just a little explanation of how does it work. And for example, if you want to use one Hadoop service on this stack, secured by Kerberos, for example, Yarn, first you have to ask to the KDC a TGT ticket. Thanks to this ticket, after you can ask a new ticket for the service you want to use. Here it's a Yarn, and after you can call your service. The problem with that is this TGT ticket expired by default after 24 hours. So for our Flink job, it's a problem because it's our streaming mode, we have no end date, so we have to find a way to renew this ticket automatically. The solution is provided by Kerberos. We can generate it thanks to the KDC a KITAB. A KITAB is a file from which we can generate this ticket. And that's the way we use Flink with Kerberos. In fact, we just have to reference this KITAB into the Flink configuration, and after Flink automatically renew these tickets. So now, how is the BI team going to manipulate our data, or store into HDFS? So
to answer this question, again, we have to look at the BI team and the tools they are using. So at UVH, they use 4 main tools and a smaller amount of other tools, which are Dataiku and Tableau to do a lot of computation, Excel also to do some reports, and a bit of Dremio to query the data and do some data mining. So we have to find a way to make our AGFS storage, basically, to be interactable with all of these tools. So the main component in Hadoop stack, which answers all of these needs, basically, is a Hive. So that's what we decided to use. So now we have to understand how our Flink job is going to write data so that Hive can read it. So let's see how to write data inside Hive. So you have 4 main vectors here that are offered to you. The first one is a CLI, like beeline. We don't care about this one because we are going to use that as inside a job. Then there is a set of APIs. We are using HDP2, so Hive2, meaning that APIs are mostly deprecated. There is a JDBC driver, and there is a file system, which acts as a backend. Okay, and here you can use Parquet or ORC. So now that we know how to write data, basically, let's compare them to what we needed to do. And here you can see that we needed to do some streaming to be performant, of course. We need to manage transaction, and because we don't like technical debt, we also want it to be future-proof. And of course, the DBC seems to fit the bill quite well. We can do one event, one transaction, so we can do streaming. It's obviously performant because it's used everywhere. It manages transaction, and it's future-proof. It's quite old, but yeah, we still talked about it. So now we decided, of course, to use JDBC because it fits the bill. But when you use JDBC with Hive, you see that Hive isn't that performant with it. Why? Because it does a lot of stuff in the backend. So when you do one event, one transaction, it corresponds to one event, 1 second, more or less. And we have 10 million events per day, which makes it so that if it's 10 million seconds, it's about 100 days. So it's a bit difficult to use for real time, I think. Also, when you use JDBC, there is another mode that you could use, which is batching. But the JDBC driver inside Hive, let's just say it's not very complete. Okay, so we can't do micro-batching, and we can't do batching. So what's left then? JDBC just doesn't fit the bill now. So let's use the file system itself, and ORC in particular. So for those who don't know, ORC, it's just a columnar-based file structure, with a lot of indexing data. That's pretty simple. So now that we know what our Flink job is going to do, and we know how our BI team is going to query the data and stuff like that, the pipeline seems to be complete. But there is still a little problem we didn't talk about yet.
So at the beginning, we only have to deal with MySQL data. We have to convert it into ORC. And in fact, at OVH, we also have to some Postgre databases. So we also have to convert this data into ORC. And in fact, when we designed this system at the beginning, we wanted to create something generic and that can handle multiple sources and things. Problem is that we have to handle a lot of data types for the different EGBD. Just for example, if we take a Boolean in PG is a Boolean, in MySQL is an int, ORC the same, we have a Boolean, sorry. And for Oracle, we don't have any standard, in fact. Generally, we use a number, but it's what we want. So to manage all of these issues, we have to create something.
So this is basically a pretty standard problem, translation problem. So we took inspiration from what already existed in this kind of ecosystem and system. We took also inspiration from linguistic itself, of course, and we created what's called a pivot format. Okay, so basically this pivot format is just a superset of all the data sets we have and can manage in the source, and also all of the data types, that we can manage in our sinks. This way, basically, what we are going to do is create a conversion from MySQL types to pivot types, and then from pivot types to, let's say, ORC types. Pretty straightforward, right? There is still a little difference, when we compare that to linguistic, is that when you do translation from, let's say, English to Chinese and the same sentence back from Chinese to English, you have absolutely no guarantee to get the same results. The cause is pretty simple. You have a lot of interpretation when you talk about languages. Here we just can't have this difference happen. We need to make sure that our MySQL source schema, when it's going to be converted to pivot and back to MySQL sync schema this time, we need to make sure that both of them are 100% equals. And this is for a very simple reason. Our pipeline here is going to be used to basically get all our data from our databases to our AGFS. but it can also be used to basically do data replication. So we need to make sure that we don't lose any information when we do this kind of data replication. So pretty straightforward, as I said. Now let's see how we use it in Flink. Again, straightforward. The collector, before doing streaming, beginning the streaming of data and executing your queries, when it connects to a data source, first thing it's going to do is dump the schema of the data source itself. Then it puts it inside our backend through an API, and then a team member is going to take the schema and manually generate the pivot format associated with it. This could be automated, but at the same time as we do the generation for two pivots, we also create the DDL associated with the sink we want the data to be written to. And once everything has been generated, so pivot format, schema, and DDL, we store that in HDFS for later use. And of course, the team members that generated the DDL also run them directly inside our sink. One other detail I didn't mention yet about our format is that it's not 100% equivalent to the source itself. We added two metadata, basically, that we need for later usage. The first one is that we are going to manipulate insert, update, and delete. Okay, so we need to make sure that all the events we are going to process inside this pipeline are processed in the correct order. Because, of course, if you update a line that hasn't been inserted yet, it's not going to work. So we added a timestamp, internal timestamp, which is going to be used later with the Flink pipeline. Also, we need to differentiate deletion event from insert or update events. The reason here is pretty simple. If we do a sync, which is a database which supports deletion, there is no need for it. But when we write something into a file, we cannot delete a line from a file. So we need to make sure that the interpreter behind that is going to understand that this line needs to be deleted further down the line. So with all of this pivot format stuff that we basically created, we now have an idea on what we need to implement with Flink. So let's see how we did it.
So let's do a focus on the Flink pipeline. First, we have to consume data from Kafka. Kafka is composed of topics, and topics can contain one to many partitions. And partitions, it's the distribution factor for Kafka. It's a way to scale the ingest. And for us, it's also the only way to keep the events ordered. That's why we use the table name in the partition key at the beginning. But the problem is the distribution. We have a bad distribution after. Why? Because due to the fact that we have, for some tables, we have more events than the others. So it's a problem inside the Flink pipeline. So the solution was just to come back to the default strategy for Kafka, just the round-robin strategy. But still, we have the problem of the order of the event. So for that, we use we sort these events and we use the watermarks, because we use the watermarks to reorder these events, a Flink feature. And we created these watermarks based on the event timestamp. So now events are sorted, and we use another feature of Flink. It's the filter function, in order just to ignore all the events that we know we can't handle after in the pipeline. So we had this one, and after, yes, our data are filtered, and now we can pass to the business of converting it.
So the conversion business, I explained the algorithm that we are going to use. So it's super simple. Just like the collector does something when it starts, the Flink job itself is going to also do something. Before processing event, it's going to go and fetch the pivot format schema inside our HDFS. And once it has retrieved it, it's pretty simple. Each event basically concerns one source table. So we basically take the subschema corresponding to this table, convert the event, this time, of course, automatically, and we push it inside our sink. Very straightforward.
So the last two steps of this Flink pipeline are aggregate and store. Up to now, we are in a full streaming mode, and at the end, we have to create ORCify. So for that, we have to aggregate events, and create some buckets of events. That's why we use the window aggregation on the Flink feature also, and we create a custom window based on function based on the number of the events and the duration. We use both, in fact. And when a window is triggered, yes, after you can launch a process of converting these events from the pivot format into the ERC format and create the ERC file. So now the pipeline is complete, but what happens if an anomalies occurred?
So we are talking about translation here. So of course, a lot of anomalies are going to occur. Maybe we are going to connect to data source where the where dates are stored in string format that we haven't yet encountered, and so our pivot format can't handle that. So there is a lot of stuff that that's going to happen. And of course, you all know the problem with that. If we plug our pipeline inside a Kafka stream, which have like 1 million events, and one is going to create an anomaly at one point, our job is going to crash, and when it's going to spawn back up, it's going to read everything from the very beginning. So that's why, of course, we are using checkpoints to make sure that we are not reprocessing data that we have already processed and inserted in our sink. One very important feature that we really love about checkpoints is that it also allows us to basically commit the offset we have reached inside the Kafka stream itself. So once we put these checkpoints, we can be sure that we are never going to go back to the very beginning. That's awesome. Everything we are talking about when we are talking about creating checkpoints, it saves as well inside our HDFS backend. So again, we use that. But what happens to these anomalies when we encounter them?
So concerning these anomalies, we don't want to lose the events that cause these errors. So for that, we use a side output feature from Flink in order just to create a new data stream when the anomalies occur. We create a new data stream, and after we can flush and persist this data onto this event onto HDFS, the events and the description of the error. And at the same time, we can create, we can push a metric, and just after can trigger an alert, for example. Concerning metrics, what we want is to have a global overview of our systems. For that, at OVH, we have a product named OVH Metrics. So we want to push all of these metrics into this OVH Metrics. Not just the Flink part, but also the collector on the HDP cluster. So we push all the metrics, and after on the Flink part, we have default metrics provided by Flink, system metrics related to jobs, and Flink gives us a way to define specific dedicated or specific metrics. That's what we've done. For example, for metrics for conversion, during the conversion based on schema, we create our specific metrics for that. So now we have to collect all of these metrics from Flink and push onto OVH metrics. For that, we use Prometheus, because Prometheus is default reporter for Flink. And Prometheus is a protocol that can be handled by metrics, OVH metrics. But we don't want to create a strong link between Flink and OVH metrics. And for that, we use a tool from the Prometheus ecosystem named Prometheus Push Gateway. And this tool acts as a buffer between Flink and OVH metrics. Just here, for example, we have two metrics. The bottom one is a metric, default metric we can find in Flink that counts the number of records in the Flink task. And the top one is one metric we define to count the number of errors due to schema not found. So with all of these metrics now, we are able to see that everything works exactly as intended.
Yeah, except that, just a quick question. How many people in the audience knows about Hive? Okay. Do you think this is going to work? Yeah, it's not going to work. Basically, everything we did here, we inserted and created some org file or C file. Yeah, sorry if I say org and shouldn't, but it's easier. So we created everything, and our metric is going to say that everything should work. But if you do a select inside your sink now, inside AGFS, through Hive or through here Hungary, you are going to see that absolutely nothing is readable by Hive. And that's for a very simple reason. When you insert data through Hive APIs or different interfaces, right? In addition to the data itself, it's also creating some metadata. And we didn't manage this metadata in our pipeline, okay? So basically, Hive cannot read and understand the file we're creating. That's a big problem, of course. But fortunately for us, Hive does have a way to read files that haven't been written with this metadata, and that's called the feature called external tables. Right. So now we have managed table created through Hive APIs, which contains some data and which are ACID, so support transaction. We have, of course, the org files that we created with our pipeline, and we can read them. We create the structure inside Hive and link the structure to the file we created. But that's also create another problem, of course. Now, for one data source, for one table in the data source, we now have 2 tables inside Hive. So which one is going to be queried by our tools? Of course, to answer this question is pretty easy. We have 2 tables with exactly the same structure. So let's do a SQL query and merge everything. Pretty straightforward. We take all the data from our external table and put them back inside the managed tables. It does the job well. But I told you at the beginning that we had like 15,000 tables. So it's going to take quite a lot of time to merge everything. Plus, when we do a merge, we cannot do a merge every second. It would be way too hard on the resources. So we decided to do a merge, basically, from half an hour to 1 hour, depending on all the table we have and on basically the volumetry and importance of the table itself. And we do that and schedule everything with Uzi, which is also on the HDP stack. So with this hack, let's say, we can now enable our BI team to basically query one table only, and they are going to have data which is not going to be real time, but half an hour to 1 hour late, which is still pretty good. And so for us and for our task management here, we could say that the job is done pretty well. Nice.
Except that the cluster is a bit on fire, because these OSI jobs consume a lot of resources, especially yarn memory. So we have to find a solution, and the solution is just to delete these OSI jobs and create the Hive data file directly from the Flink pipeline. So just a little explanation about Hive data file, and especially the Hive metadata. If we select data from your transactional ORC transactional table, yes, we can get the values from your different columns, but in fact, we can get also an attribute, a column named row ID that is hidden by default. And in this row ID, you can see the different the Hive metadata, a part of the Hive metadata. Inside this metadata, we can find the transaction ID. One attribute is a transaction ID that, in fact, is a transaction created by the Hive metastore when this record was created. So now let's switch to the file view on HDFS. So when we execute an instance statement into a transactional table, a seed table, first a transaction is created by the Hive metastore. This transaction ID is put in the file name, but this transaction ID is also put into the Hive metadata, besides the real data, in fact. And after we can find 2 attributes: original transaction and current transaction. For an insert, the value is the same. We put the transaction ID created by the metastore, and we put this value into these 2 attributes. For a delete, it's not exactly the same. Yes, we create also a new transaction, and this transaction ID is put into the current transaction attribute. But into the original transaction, we have to put the transaction ID created for the insert. So that means we have to keep track of all this data, of this Hive metadata, during the ingestion, during the pipeline. And for that, we create a Java object, Hive meta, in order to store this data, and we put it into the Flink state, because Flink state is available from the different task. Up to now, we use the default the file system backend for to store the state, but now we have to find something more scalable, in fact. So we use RocksDB. We use RocksDB as a backend for our Flink state, because it's scalable, can distribute different instances of RocksDB into the different task manager. RocksDB is incremental. That means when we create the checkpoints, we don't have to create a snapshot of all the state, but just the delta. And RocksDB, we have the locality. That means, yes, task manager can handle a copy of RocksDB data, and that avoids the need to get data from HDFS, for example. So it's more efficient. So now we have a full pipeline with numerous jobs. We can create Hive data file directly from the Flink pipeline. And just as a reminder, the different Flink features we use to create that allows to create this pipeline. The first watermarks just to sort the events, the windowing for the aggregation, and after the RocksDB for its scalability, first checkpoints, side output for the anomalies, and metrics. So all of this allows us to manipulate our data with as little resource as possible.
So this pipeline is now in production. So I told you at the beginning that we had 15,000 tables for 200 databases. We don't need all of that for our BI team, so let's just put some numbers to show you the size of our cluster and stuff like that. So from the 15,000 tables, we have 2,500 that are synced at the moment inside our sync. They still contain about 3 billion rows, and still get about 10 million sevens. Of course, the one we need for our BI team is, of course, the ones that have the most manipulations. When we do a dump, some tables we are going to dump are going to contain up to 300 million lines. So our pipelines need to be able to handle 10 million 7 per day, plus potentially 300 million, when we do a dump at the same time as we do some streaming. So it's quite, well, for us anyway, it's quite a large pipeline. And still, to manage it and make it run, we only need about 100 jobs, which runs in about 200 slots. So pretty small cluster, pretty easy to manage, even on Yarn. So basically, we are really, really satisfied by the work we did, and of course, the capacity of Flinks. So that's the pipeline we created. It's in production. It works just fine. Let's see just what we want to improve now. So I said that we are using at the moment stack HDP2. We would like to go on Hive 3, and so we need to move to either Cloudera or HDP3. Why Hive 3? For a very simple reason. Hive 3 basically reintroduced the streaming API. So we could basically throw everything we just did with Delta file and stuff like that for just using the Hive 3 API to do streaming. So that would simplify the job itself and make it a lot easier to manage. We have also some features that we would like to add to our pipeline. First one being real-time data merging, so to basically pre-process data for our BI team before they do the query in the sync and stuff like that, create new structures. This is kind of easy to do, but we still need our BI team to give us some, basically to tell us what they want to do in the end, basically. So we are waiting for them on this side. Also, what we would like to do really is give them even more hands-on on our pipeline, and so create some kind of rule engine. And with this rule engine, we can definitely think about pretty easy usage, like data anonymization, for instance. But we have also a machine learning team at OVH, and so we could basically plug in some algorithm to do some categorization on data, for instance, as close as the source possible anyway. I talked also about so a thing for Hive 3. I just did here that we want to create. We talked about the ORC sync. I also talked just quickly about data replication. So we could create here a thing for MySQL, we create a thing for Postgres or whatever we want, basically. So this is also something we are studying at the moment and doing when we are required to, of course. There is a lot of manual labor still involved in our pipeline, like DDR generation and DDR run inside our things, or of course pivot formats, schema generation. We obviously want to eliminate that. So as soon as we can, we are going to focus on that. It's mostly done on the pivot generation, but still the DDL has some work to do. And the last big point we want to make here is that this pipeline is, of course, very interesting for us, and we think it might be interesting for others, so we are trying to make it open source. I say trying because, of course, it's very OVH-centric at the moment, so we have a lot of cleanup to do and generalization and stuff like that, but as soon as we have a version ready, it's going to be open sourced, and that's about it. So that's it for our presentation of the pipeline we use at OVH for basically real-time BI, or as close as we can anyway. I hope you learned something and found it interesting. I think we have about 5 minutes for questions, so shoot if you have.
How do you manage schema changes?
So that's kind of a problem at the moment. Schema changes, we have a policy first inside the team that when a schema is going to be changed, the team in charge of the data source is going to tell us that they're going to change it so that we can manually change the structure inside Hive, for instance. Also, we are reading bin logs, for instance, from MySQL, which contains the LTR. So this we can manage on our own. We can't do that, for instance, with Postgres, because in the logical decoding that we are using, there is no LTR. So yeah, we are dependent on human interaction again to make sure that we get the right stuff. Otherwise, it's going to create anomalies, and in the side output, we are going to be able to see that yeah, we can't handle that and see what to do.
Thank you. Thank you for the talk, guys. You've done an outstanding job. Please make it open source. What's the size of the largest table you imported? Like 2,500 tables is like pretty good number, but
yeah.
if they're relatively small?
No. Basically, the biggest one have, I think, about 1 billion rows, I think, the biggest one. Maybe even more, I think, because yeah, we exist from 1999, so of course the biggest one is going to be the billing one. Yeah, I think we have one which is even bigger than that, but mostly it's around several million, several hundred millions in average. We have, of course, smaller ones for referential and stuff like that, and yeah, I think the biggest one is 1 billion, 1.5 billion, something like that.
Hundreds of millions rows and rows of several megabytes.
Yeah, that's our team lead, so he knows better. Does that answer your question? Sorry. Yeah, okay.
Why external table doesn't suit you? Why you need these merging processes? I have not really.
Basically, just because it was easier for our BI team to only query one table. That's about it. We could have done that, but yeah, actually we could have done that. Yeah, maybe you can add something. Maybe.
Can you activate? Yes, thank you. Could you repeat just? I don't understand. Just.
Why you need Hive managed table? What's the problem with external table that doesn't suit you?
Because we have to at the end we have to provide the transactional way for transaction table when we can't create directly from the Flink pipeline.
The question, I think, is more like, why didn't we use only external table? What did we find? What do we do? Why?
Why we use a transactional? Because it's a feature we want to use, because all the users on the BI team, we want to have a transaction AC table. In fact, at the end, we have to manage with a transactional way all the the way to use this data. So for that we use also it's more efficient for we benefit from the optimization from the Hive that we don't have with external table. It's not because, for example, with the external table, we have to scan all the HDFS directory. So with the transactional, with AC table, it's more efficient due to the fact the transaction ID. There are some optimization that can skip data when the Hive has to scan all the HDFS data, the HDFS directory for the different buckets.
Okay, thank you.
Do you have any?
Do you have any validation process for the results, maybe due to the compliance reason or whatnot?
Validation process, you mean?
Yeah, like for instance, that everything which was changed was actually delivered, for instance. I mean, like I know Flink exactly once, right? But things might go wrong.
Basically, our BI team does have a lot of process to make sure that we have several pipelines running in parallel. That we have a legacy one, basically, which runs basically by hand. And we have this one, and we use both of them. One is temporary, I think, just to validate that all our data are okay, I think. And we don't have any process inside our process itself, our pipeline itself, to make sure that the data is inserted correctly. But because we are all managing everything by transaction and stuff, we are almost certain that everything is accurate enough. Anyway.
Besides this pipeline, we created some tools to validate the different steps. So we have a lot of metrics. Yes, of course, but we create also some. We use some other table just to validate the different. For example, the data collector push some metadata, and after the Flink pipeline put also some data, and after we have tools that we can know to see where is a potential problem, and yes, metrics plus some tools. In fact, some tools we can just to validate the process.
I think we need to wrap up because we are out of time. And please thank the speakers. And if you have some questions, please reach them after the talk.
Thank you.